Good afternoon, I'm Christine Sa. Welcome to this news briefing from the 250th National Meeting and Exposition of the American Chemical Society in Boston. We're joined today by Dr. Ben Lever from the Air Force Research Laboratory at Wright-Patterson Air Force Base. He'll be talking to us about his work on flexible electronics. Dr. Lever.
Thank you. Good afternoon. This morning at the ACS National Meeting, I spoke about some work that we're doing at the Air Force Research Lab related to flexible hybrid electronics. I just want to briefly explain the concept of flexible hybrid electronics. Relatively simply, it's the idea of taking high performance yet also flexible electronic devices. These could be CMOS semiconductors, for example, that can be made very thin, just a few hundred nanometers thick, so that they're highly flexible. Combining those with other components such as batteries or sensors or interconnects that can be printed, and putting this combination of devices onto a non-traditional substrate. So this could be like a plastic that could be stretchable or conformal. I have shown on this chart next to me a few different applications that the Air Force sees for flexible hybrid electronics. It's really quite exciting, and we think is going to revolutionize electronics for the military, but also for a lot of consumer electronics applications. Just one quick, I'll go over a few quick examples. One that's really exciting for me is the idea of human performance monitoring or airman performance monitoring for the Air Force. This is the concept of people or airmen wearing a sensor patch that would be something like a Band-Aid that would be on an airman's shoulder. And this could provide the commander or the individual, him or herself, information about the hydration level of that person, or if that person is fatigued or his or her cognition is impaired. This could obviously have a lot of applications in the medical field and also in just sporting activities. Secondly, we're interested in electronics that could conform to the shape of a wing or to the inside of an airplane, as an example, to make electronics lighter. You could think about adding an antenna or a communication capability to an aircraft where the antenna just conforms to the shape of the aircraft. So instead of adding a new structure to the exterior, which could cause drag, you could just have a conformal antenna that's printed on the vehicle itself. I'm going to show a video in just a moment about the work that they're doing toward more resilient or survivable electronics. I'm going to I'll show you the video, which really speaks for itself. And then finally, we're doing a lot of work in power and integrating thin film power into new devices. So just give two examples of some of the research that I talked about this morning. The first is this idea of indium-gallium liquid metal alloys. So if we all think back to the Terminator 2 movie from 15 years ago or so, there was the Terminator guy who was basically, we all remember the liquid metal shape, and after he was broken into a bunch of pieces, he came back together, for those of us who remember the movie. The similar idea with this liquid metal alloy that's been demonstrated by Michael Dickey at North Carolina State, it can be used in applications such as stretchable electronics that's shown at the top of the screen here, where instead of having a solid interconnect or a wire that once you start to stretch it, it will break, you could have a liquid metal that's acting as that interconnect, and so as you stretch it, it just fills the space in your material. And then it can also reconfigure, which is shown at the video at the bottom of this screen. You could, again, we in the Air Force, we think about antennas, and we could have different antenna patterns on the exterior of a vehicle, and just by pressing a button, let's say the pilot could reconfigure the shape of that antenna to enable a different functionality. I briefly want to end with a second application that we're working on. This is for more resilient electronics. So electronics for the Air Force have to really withstand incredible different environments, both with temperature and also different shock and vibrations. So for those of you that can see the video, on the left side of the screen, there is a traditional circuit board that is subjected to about 20,000 Gs of shock. This is the kind of shock that a weapon might experience when it hits the ground. In some cases, we want the electronics in that weapon to survive the initial impact. And you can see that with traditional electronics, that's not going to happen. The components are just going to fly off the circuit board. Whereas with the electronics on the right side of the screen, this is actually a flexible circuit with it's a flexible substrate and a flexible integrated circuit subjected to similar kind of stress, and you can see that it survives that kind of impact. So there are a lot of applications that the Air Force sees for this, and of course all of us who use consumer electronics will also benefit from it, from having electronics that can survive a fall, but not having the thick packaging that's on all our devices now. So we could have very, very thin electronics that conform to the shape of our bodies, but are also very, very survivable and rugged.
Thank you, Dr. Lever. Do we have any questions? Oh, and if you could wait for the microphone to ask your question so our online audience can also hear your questions, and please state your name and affiliation.
I'm Doug Smock with the Molding Blog. What are the plastics that you're working with, Dr. Lever?
So we've looked at a number of plastics. So we focus primarily on plastics that are bendable or stretchable. So they could be elastomers, like a silicon-based material, like a PDMS, or something that's just... It's PDMS. Yeah, I could get the specific name for you. But it's a silicon-based polymer, silicone-based polymer. We also look at a material like a polyimide, a Kapton, which is also flexible. The printing approaches that we use, although you have to tailor the printing process for whatever polymer or material that you're printing on, they can be, that's something that we can do and that we do regularly, is tailor the inks or the printing process to a specific plastic.
Other questions?
Bill Buslik, ACS News Service. How much deformity do these materials can tolerate? Like, I can understand the substrate being foldable, bendable, whatever, but the electronics, which is minuscule on the surface, the abstract says that you can fold them, but can you actually crumple them and still function?
That's a great question. It depends on the type of electronics that we're talking about. So I think crumple would be a pretty extreme case. And it might be that, so we envision, when I talk about flexible hybrid electronics, again, the idea is that some of the electronics are high performing. They could be silicon based, and other parts of the device could be printed. And so I think the simplest answer is that I would expect the printed components to be much more rugged or durable than say, the materials that are based on inorganic semiconductors like a silicon CMOS thin integrated circuit. So I think that's exactly what would happen. If you were to crumple something, hopefully it would be designed in such a way that, like you say, the silicon parts could be so small that the crumpling doesn't damage them. And the rest of the components would have been designed in a way specifically so that they can survive that kind of strain. And just to maybe briefly expand on that a little bit for what kind of strain we would like some of these materials to be able to withstand. When we talk about a sensor patch type of application, again, this would be something that would look a little bit like a Band-Aid and worn on an airman's arm or an individual's arm. You could think about this at a hospital. Skin typically stretches about 30%, so we want the device to be able to stretch, at least as a whole, to be able to stretch about 30%. The example that I showed on the chart actually showed about 100% stretching for that device.
We have got a question over here.
Thank you. Ben Valsler, Chemistry World magazine. This sort of follows on from what Bela was asking. You mentioned earlier semiconductors. The abstract in here talks about a nanotube-based battery that you've been able to build as well. What components for circuits can we currently make flexible, and which ones are still the old silicon stiff ones?
Today we can make almost any component for a circuit flexible. There are just limits. And I would say there's also an important distinction to make between something being printed or just flexible. And we can print almost any component of a circuit today. They just the printed components typically just don't have performance that is high as the traditional electronics, like some silicon-based electronics. But we could. I think it's fair to say we could print an entire circuit and the entire circuit would be flexible. It just might not be adequately performing for demanding Air Force applications or consumer electronics applications, which really gets us toward the idea of the flexible hybrid electronics, where we combine the printed and thin traditional electronics. Does that answer your question?
I think so, yeah. It's things like transistors. So when we've talked about flexible electronics before, they have usually been the wires that are flexible, but you still have the problem of having bulky transistors that ultimately are going to present mechanical problems with the repeated use. But it sounds like you've got around at least some of that. It's just they may not be quite as good as that bulky transistor would have been.
Right. At AFRL, at least in our group, we don't print transistors, but there's, I'm sure, plenty of work that's going to be presented this week about printed transistors, but they don't have the same kind of functionality as a CMOS silicon transistor. And they're not used for processing. They might be used for data storage or for displays or something like that.
And the printing side of it sounds like you can make very bespoke devices for very particular situations that have very particular challenges. I guess the other side of that is making commonly used parts so that you can start to deploy this technology cheaper and more widespread by standardization. Is that also something that you'd be looking at, or are you, because of the military requirements, are you really looking at bespoke exactly for that requirement?
So I think that's a great question. I think the question could be what's the value of printing electronics versus mass production of electronics? And so I guess I would answer that in a couple of ways. So first, an advantage of printing or additively manufacturing anything is that it can be tailored when you need to have specific properties for a specific application. And the example of airman performance monitoring, different individuals are going to have different levels of biomarkers in their sweat or other bodily fluids. So it might be needed that you tailor a specific sensor that's printed in a certain way for an individual or a group of individuals. So if printing is part of your fabrication process, then you can make small changes in between different lots or individual components so that you can tailor it for an individual if that's what's needed. So that certainly could be of interest. I guess secondly, I think we all know that the military is a very small customer for a lot of the large companies, and so printing could be, although it might not be the cheapest overall, if we were thinking about how do we want to make 1 million of something, well, then of course we want to use traditional roll-to-roll processing, mass production. But the military might not need 1 million of something, so it might actually be the most cost-effective way to buy 1,000 of something, because it might be very expensive to design all the equipment, to fabricate all the equipment that's going to make the device that we need if we only need 1,000 of them. And the last thing I would say is that it's something that, although we don't work on at AFRL, it's something we're very cognizant of, and that's the challenge of scaling up the processes that we work on. And although today we work on printers that don't look that different than inkjet printers that we're all familiar with, that we've seen in our offices, everything that we do, we think about how it can scale up. And so even though today it's a small process that's on a desktop and it's not super fast, over time we see that scaling to, because everything is solution processable, it can potentially go to roll type of approaches in the future when that makes sense.
Okay. And just one more question, if you will. I'm interested to know what the balance is between Air Force research and academic research. So what is that relationship like? How much of this is purely Air Force research? How much is things that you've discovered out in academia and brought in, and how much has the Air Force actually sort of funded research in academia in order to develop from it?
That's a great question, and I'd probably have to go by on a case-by-case basis to explain where this particular technology originated and what part Air Force researchers contributed versus researchers at universities. But the Air Force Research Lab, even among the Department of Defense labs here in the United States, is somewhat unique in that within one organization we do in-house research. There's part of AFRL that funds universities, and we also fund companies to do work. And so within one organization we do all three of those, and they don't happen on their own. So what we find often we get the most return if we're doing in-house research or work that happens at AFRL in partnership with a professor at university, or it might be separate from work that we're also funding in industry. But the idea is that we're doing collaborative work with our industrial and academic partners so that we can, again, transition the technology that you work on to consumers, and so that we're also pulling in information from academia rather than repeating or duplicating work that's happening there. But I also want to emphasize a lot of the work that I spoke about today. So the video I showed of the electronics flying off of a circuit board, that was done. Those videos were taken at our munitions directorate that's in Florida. The sample that was tested next to it was fabricated by my colleagues. And the liquid metal work that I featured, all those videos were taken by my colleagues. All that work was done at the Air Force Research Lab. Although that work, a lot of the pioneering work was done by Michael Dickey at North Carolina State, who we're collaborating with.
Do you have any other questions? Yes.
Doug Smock again. How close is your research to actually evolving into a real actual part?
So I think different aspects of what I talked about today are different. We use the term technology readiness level in the Department of Defense. So one thing that I can say that is quite mature, I talked about conformal antennas. And so these are the ideas of, this is the idea that you could you could print an antenna on a fuselage or wing of an aircraft, as an example. This is something that has been demonstrated. We've done a project with that recently, but 10 years ago this was shown, and actually Boeing and other companies are using those kinds of concepts of printed devices or printed electronics that are on vehicles today. So some aspects of what I have talked about are very mature. There are companies, I'll just use the example of MC10, which is based here in Boston, which is working on different concepts for wearable electronics today for monitoring. You can go to their website and see different demos of what they're doing, but they're looking to commercialize this soon. We also have a program with them that's based on demonstrating a hydration monitor that a soldier could wear that would provide an indication of how hydrated that soldier is in advance of a point where I should say airman, that in advance of when that airman would become dehydrated and his or her life could be in danger. So there's certain aspects that are mature and ready today. Now certainly the liquid metal work that I talked about, that is much less mature. That could be 5 years or more before we could think about turning that into a product. So it really, again, is dependent on the specific technology that we're talking about.
And have you considered use of conductive plastics at all, particularly for what you called the thin film flexible power?
Yeah, I'm not exactly sure which specific conductive plastics that you're talking about. I would say that there are, for example, conductive epoxies that are out there right now that are commercially available. I would say in general, the conductive materials that are available today are flexible but not stretchable. And so that's a key challenge that we're trying to address with some of the new formulations that we're working on, is having conductors such as an interconnect for two different devices on a plastic stretchable substrate, that we could stretch that substrate, and that interconnect itself is going to survive that stretching. And I'm not sure that there's anything that's commercially available today that's going to be survivable.
And could you give a little more detail on the 3D printing technology that you're using?
We use a number of different approaches. So it could be something that's as simple as a filamentary approach, and there you can imagine having a syringe that is kind of automated in how it dispenses, and so it's a fairly simple printing approach. We also use a technology called aerosol jet, made by a company called Optimec. This is an off-the-shelf approach, and it's a fine aerosol spray that you can print features as small as about 10 microns. We use inkjet printing, which is essentially the same that's used for graphic technology, but we can do a number of different functional inks that are metals or polymers or ceramics or other materials. A fourth commercial system that we have is called micro-dispensing. It's an N-script system. This is a attractive printing approach because with one printer you can print materials that have viscosities ranging from water to peanut butter. And so why that's interesting for the Air Force is because we could print something like an epoxy, which could be used for a composite material, a structural material, and we could print that epoxy, and then right on top of it we could print something metallic, like what would be like a wire or an interconnect, and then we can print more epoxy. So in the end we have electronics that are embedded in structures.
And would you also explain again what exactly you are printing, what material you're printing? It's not a plastic, is that right?
So we're printing, we can print plastics, and we do print plastics, and they could be some of the same plastics that I mentioned earlier, like the elastomers or other materials that we print. Primarily, we're printing inks that are conductive, although we also print dielectric inks, so non-conductive inks, insulating inks for example, for a printed capacitor. So mostly we're printing silver inks that are based on silver that are conductive, and so they could be silver nanoparticles or silver microflakes. And in the case of wanting to have a stretchable silver ink, it could be something like a silver microflake that's in a polymer, and so that the polymer gives it some kind of stretchability while the silver component makes it conductive.
All right. Thank you, Dr. Lever. I think that's all the time we have for this press conference. Thanks so much for joining us. The archived version of this session will soon be posted at bit.ly/ACS Live Boston. Please join us for our next press conference today at 1:30 p.m. on how urban grime is contributing to air pollution. Thank you.